Hi, my name's Braid MacRae. I'm here representing Human Aerospace and RMIT University. On behalf of the team, I'm pleased to be talking about mechanical loading countermeasure suits. So the reason I'm talking about that is that we've got three wider projects going on at the moment. Two of them are looking at developing prototypes for countermeasure suits, one being a sensory motor suit and the second being an orthostatic intolerance garment. The third project is looking at advancing the concept of mechanical counterpressure EVA suits, and here at ASBX, John Clark is talking about the EVA suit, but here I'm talking about mechanical loading in the context of countermeasure suits. I'll start off with an introduction to countermeasure suits that utilize mechanical loading and talk a little bit about some of the properties that are required. I'll touch on why countermeasures are needed, revisit some applications of mechanical loading countermeasure suits, and then finish off with an outlook. Here are some examples of countermeasure suits that have been used in space. On the left there is the Russian Penguin suit that's been deployed for a number of years now and is currently available on board the ISS. In the center is the gravity loading countermeasure skin suit that's been trialed twice. And on the right is an example of an orthostatic intolerance garment. When using suits to apply loads to the body, we can consider two general forms of loading. Axial loading is shown on the left there, where the load's applied in the body's GZ axis, and circumferential loading is shown on the right there, where the body's effectively being wrapped in the suit itself, and the resultant force is normal to the body surface, which manifests as compression to the body surface. Both the Penguin suit and the GLCS utilize axial loading, and a key purpose there is to restore or partially restore the static musculoskeletal load associated with the body's weight here on Earth. Of course, when we're exposed to a gravitational field, the weight experienced at any vertical height of the body will result from the sum of the body mass above that given point. And hence, if we consider both legs together and a standing person, the axial load will be lowest at the top of the head, incrementally increasing towards the soles of the feet. The Penguin suit uses a bungee and harness system anchored at the waist, which results in this two-stage axial loading characteristic. Compared to a 1G load here on Earth, you end up with a relatively higher load at the shoulders and relatively lower load at the feet. From an adaptation standpoint, the load itself isn't necessarily a problem, as load thresholds for given outcomes are not yet clear, but compliance is reportedly an issue, in part due to the discomfort of the high shoulder loads and the waist belt itself. The GLCS was designed to overcome some of these limitations and more faithfully replicate the 1G gradual increase in load experienced by the body here on Earth. Instead of using bungees, the GLCS utilizes the elasticity of the fabric itself. When I'm worn, the suit is smaller than the body, so you can imagine it being stretched in both directions during the donning process. The vertical stretch is what results in the axial load, while the horizontal or circumferential stretch is what anchors it to the body, in effect replacing the single waist belt of the Penguin suit. With the circumferential stretch being used to anchor the suit to the body, it's no surprises that the GLCS also shows up here under circumferential loading or compression. The other suit you can see there is, of course, the orthostatic intolerance garment. I'll go a little bit into the function of this garment later on, but here I just want to draw your attention to the outcome of this circumferential loading, which is the pressures that are being applied to the body itself, and that there are particular characteristics, particular profiles that may be targeted using a suit like this. For example, here we can see that the pressures down around the ankles are about 55 millimeters of mercury, and that progressively decreases as you approach the abdomen, and the abdomen pressure itself is about 16 millimeters of mercury. Irrespective of the direction of the loading we're trying to achieve, the underlying process is the same, and that's stretching the loading element. Usually that's elastic materials in these suits. So in the Penguin suit, it was the bungee cords, and in the GLCS and in the orthostatic intolerance garment, it's the fabric itself. And so there we start with the material. It gets stretched, and we end up with this restoring force that acts to want to return the material back to its original dimensions, and it's that restoring force that we're capitalizing on in these garments. Because the absolute force will depend on how much of the fabric or material you have, it's more informative to normalize it to either the width or the cross-sectional area of that fabric or material, shown here as tension or stress. And we can be more specific when referring to the stretch and refer to it as a strain, which is the change in length divided by the original length, expressed either as a ratio or you can convert that to a percentage. And we can characterize the stress strain or tension strain relationship using instruments like a tensile tester. In order to design suits to apply specific loads to the body, we need to understand certain mechanical properties of the fabrics or materials being used to make those suits. And on that, there are a couple of key features I want to highlight. One is defining the modulus of elasticity to be used to convert from the target stress or tension to its corresponding strain. And the other is utilizing anisotropic or directional properties of those fabrics or materials. To the first point, here is an example tension-strain relationship for a particular fabric that's been subjected to a single cycle of being stretched through to 25% strain and then allowed to recover. There are two parts to this extension and recovery relationship, with the increasing tension following this path here and the decreasing tension following this path here, and so that's just a classic hysteresis behavior. So using different samples from that same fabric type, if we stretch it through to 50% strain, 75% strain, and 100% strain, we can see that it doesn't matter to what strain this fabric has been cycled to, the increasing tension always follows that same path. This would be convenient because it allows us to go from a particular target tension through to knowing what the target strain has to be in order to achieve that tension. So when you're designing the suit, if you know a particular load that is required at a particular site of the body, you need to know how much to stretch that particular loading element, and this relationship is what you use to go from one to the other. However, if we go beyond the first cycle, so this is looking at cycle 3 at 25% strain, 50% strain, 75% strain, and 100% strain, we can see that the extent to which the fabric has been cycled is influencing that tension-strain relationship. So here they're not following that same path irrespective of the strain they're being cycled to. And as you've probably picked up, the number of cycles also has an influence. So in red there is the first cycle, and in blue is the third cycle, each being cycled through to 100% strain. And the change that happens there between cycle 1 and 3 becomes incrementally smaller the greater the number of cycles the fabric is subjected to. So here we can see that it is quite important to understand the tension-strain relationship because it has implications for designing the garment in terms of the size required and the eventual loads that are achieved. So if we take our 60% strain we identified before of that first cycle, we can see that this might actually have reasonable implications for achieving a target tension in the end suit itself. The second key feature worth highlighting is this anisotropic property, in which the direction that the fabric has been stretched influences that tension-strain relationship. And this can be capitalized on in the design of the garment. For example, if you have an orthostatic intolerance garment, you want high circumferential tension but low vertical axial tension. But when you have something like a knee and it bends, you get a stretching of the fabric in that vertical direction. And in order to facilitate movement and comfort, you don't want that tension to increase too much during that movement. So you can look at these tension strain relationships and choose the directions that would best facilitate that particular purpose. Now that we've got an idea about some of the material properties, we can look at how they interact with the size and shape of the body itself. For this example, I'm going to be using compression being applied to the surface of the body. And in that scan, if you can imagine a cross-section being taken at the level of those arrows. For now, let's assume that the circle represents our cross-section and the black line there going around the circle is our fabric of the suit itself. Then using the radius of that cross-section and the tension of the fabric, we can estimate the pressure that's been applied to the body. If our cross-section is actually perfectly circular, then that pressure is going to be uniform. But life's never quite that easy, and let's say our cross-section looks something a bit more like this. Then with the variations in the local curvatures, we actually end up with variations in the local pressures. And using this approach, those local curvatures and local pressures can be modeled in more detail. Furthermore, we know that the body won't necessarily stay the same size and shape with duration and space, or indeed with the application of the countermeasure suit itself. And two things that might happen are rounding and scaling, and both of these can be modeled as well. And so with rounding, the increasing roundness of the cross section as it tends towards a circle, you get an increasing pressure uniformity, as I mentioned before. The other thing that can happen is the scaling where, for example, with muscle atrophy, you get a decrease in that cross-sectional area and the circumference of the particular body site. And if that was the case and you had a garment that was still the same size, it wasn't being adjusted, then you would expect a decrease in pressure with that decrease in cross-sectional area or circumference. It'll come as no surprise to the audience here that space is a hazardous place. And the hazard of altered gravity is a key one with respect to the countermeasure suits that I've been talking about here. Altered gravity with space travel consists of prolonged or acute exposures. So with prolonged exposures, the typical ones there are, of course, microgravity of transit in orbit, 0.17 g on the moon and 0.38 g on Mars. And sustained exposure to this altered gravity will drive physiological adaptations that will be functional for that gravitational environment, but may become dysfunctional for a transition out of that gravitational environment. And with respect to acute exposures, key examples there are the G loading during ascent and descent. Speaking of changes that happen, here are some examples that occur with exposure to microgravity. I'm sure other talks here at ASBX will go into some of these in more detail, but here I just want to highlight that changes occur pretty much throughout the body and that these are often integrative in nature. For example, demineralization of terrestrial weight-bearing bones not only impact the bones themselves, but can lead to other issues such as increased likelihood of kidney stones. So with those changes that occur in lower gravity, that leads to implications for returning to higher gravity environments. And so that includes lower microgravity of low Earth orbit, transit, or lunar or Martian surfaces, all having implications for returning to Earth. And the microgravity during transit or, for example, outpost orbit has implications for lunar or Martian surface exploration. And there on an operational side, the astronaut may have or is likely to have reduced physiological performance capacity for a period there. So an allowance may be required for reconditioning, where a reduced workload expectation is placed on the individual. Otherwise, you might see an increased likelihood of accidents or injury, or a decrease in capacity to execute routine or emergency tasks upon or following planetary descent. And of course, those changes also have implications for return to life on Earth. And for example, with that bone loss, the duration to recover bone loss is typically longer than the duration of the space travel itself. One key influence of that unloading of the gravitational field includes the redistribution of blood and other fluid within the body. Here on Earth, as indicated in the image A on the right there, our body is used to dealing with the hydrostatic effects of 1G, whereby our cardiovascular system works against gravity to return blood to the heart from anywhere below the level of the heart, and works against gravity to maintain adequate flow to anywhere above the heart, for example with cerebral perfusion. Then transitioning into microgravity, we lose that hydrostatic effect of gravity, and the large gradients our body is used to dealing with has suddenly been removed. Quite quickly there, we get this headward shift of fluid, whereby there is a reduced volume in the legs, and this congestion and puffiness of the head and face, which leads to a compensatory loss of plasma volume, shown in C. So that loss of blood plasma volume and the lack of having to deal with blood pressure challenges leads to a condition, or the increased likelihood of a condition known as orthostatic intolerance. And that's essentially an inability to maintain blood pressure when upright, when re-exposed to a gravitational field. Orthostatic intolerance itself is multifaceted, but as I say, that hypovolemia or decrease in plasma volume is one of the key contributors. And there, upon orthostatic challenge, such as standing upright from sitting or lying down, you end up with a drop in cerebral perfusion pressure and flow, which can lead to presyncope and syncope. And for that reason, orthostatic intolerance garments are used operationally, and that's usually in flight, so on the return to Earth, for example, and they may be worn in that initial post-flight period. Being upright under the influence of a gravitational field, we end up with pooling of blood in venous reservoirs, and it's these reservoirs of the abdomen and the lower limbs that are targeted with orthostatic intolerance garments. As I mentioned before, these garments are worn during and often following the Earth re-entry period, but they may also be relevant for lunar or Martian ascent or descent, particularly if the vehicle places the individual in an upright position. And the reason there being that this vertical position is the most challenging for the body to deal with orthostatic challenges arising from G-loading or gravitational fields. The previous orthostatic intolerance garment or anti-G suit used by NASA was worked with air pressure, so it was a pneumatic garment, which was really effective at maintaining the function of the garment in terms of preventing orthostatic intolerance, but it became problematic when you tried to move in the garment because it was stiff with the air pressure when inflated, and once it was detached from the vehicle airline, then it would deflate over time and thereby losing its function. So both the contemporary NASA and the Russian orthostatic intolerance garments use fabric tension to be applying that surface compression. And these garments are effective at maintaining blood pressure and flow on exposure to orthostatic challenge, but there are some areas for improvement, and those include improving the comfort, particularly for prolonged wear during re-entry in the seated position, improving the sizing in terms of reducing the imposition on the end user, and facilitating adjustment of the garments in terms of being able to accommodate the changes in limb volume, for example, that occur with duration in space. And finally, clarification of the pressures in terms of lowering the pressures improves comfort, but the pressures still need to meet a certain threshold in order to maintain function of the garment. So finding the balance between the two there is very useful. The musculoskeletal system is influenced by that reduction in gravity, in this case exposure to microgravity. Some of the key changes observed there include demineralization of weight-bearing bones, atrophy of so-called anti-gravity muscles like postural muscles, and increase in stature resulting from a loss of curvature of the spine and probably some swelling of the intervertebral discs. Both vestibular and non-vestibular aspects of sensory motor function are influenced by this reduced gravity environment. Here I'm just going to focus on those non-vestibular changes. So there is unloading of the body and unloading of several sensory afferents, including the soles of the feet, as I mentioned before, and also a change in proprioception whereby the body weight is unloaded, and therefore things like the force required to move a limb changes. There's a central reinterpretation of the sensory inputs, and these lead to changes that result in postural and locomotion issues when returning to a higher gravity environment. This is an example of the magnitude of some of the changes that can occur with exposure to reduced gravity. So here we're looking at aerial bone mineral density and the changes from pre-flight values following flights lasting 4.5 to 7 months. So some of the key sites there are the femoral neck and the proximal femur, where those reductions in aerial bone mineral density are up to and exceeding 8%. At the moment on the ISS, exercise equipment is a key part of the countermeasure suite for mitigating these sorts of changes. However, it's not clear what or if any exercise equipment will be available for lunar and or Martian missions, and so therefore other countermeasure approaches may become more important for addressing that deficit in availability of exercise equipment. To that end, this is NASA's Human Research Roadmap risk matrix. And here we're looking at the risk of bone fracture due to spaceflight-induced changes to bone. So as mentioned before, exercise equipment on board the ISS is quite good at mitigating some of the changes like demineralization of bone. So you can see up the top left that low Earth orbit, even long missions have a low risk associated with it. But as we go down, you can see that lunar, orbital, and surface and Martian missions have an increase in risk, and that is contributed to by that uncertainty with exercise equipment availability. And here we have the risk of altered sensory motor or vestibular function impacting critical mission tasks. So things like a control of a vehicle or mobility during an emergency egress of a vehicle might fall within the scope of this risk matrix. And again, we can see that the lunar orbital and surface missions have quite a high risk associated with it, and long Martian missions as well. And back to our mechanical loading countermeasure suits. So these suits may be used for loading the musculoskeletal system and or contributing to sensory motor preservation in terms of loading the body in the axial direction for loading the spine, for example, and promoting bone health, but also in terms of loading the soles for stimulating those mechanoreceptors in the feet. And there we are currently developing a sensory motor specific version to augment some of those sensory motor effects in comparison to the penguin and the GLCS. And there we are looking at covering more of the body and employing some different techniques in terms of stimulating some of those mechanoreceptors around the body, and also trying to target that proprioceptive function in terms of adding resistance to movement. The wear protocols of these types of countermeasure suits may be either prolonged wear, where it's a wear and forget sort of a setup where you are doing your daily activities while these suits are doing their thing, or it may be that specific sessions are used in terms of having a set routine and combining with particular activities. Development of these suits certainly doesn't happen overnight, and here is an example with the GLCS and its pathway from Mark 1 on the left through to Mark 6, which was flown on board the ISS in 2015 and 2016. So this suit has been contributed to by a number of groups internationally. The original suit on the far left there was targeting full restoration of Earth equivalent body weighting of those weight-bearing musculoskeletal elements, whereas the final version that was flown on board the ISS was targeting the spine specifically. And there it was found to partially reverse an increase in stature, and that is potentially due to compressing those intervertebral discs, so reducing the swelling of those discs, and or restoration of the curve of the spine. In terms of outlook, there's plenty of scope for countermeasure suits like these. Advantages include their low mass and low volume. The GLCS is promising for spine health and for providing some stimuli to the soles of the feet for promoting sensory motor function. And so we believe there's more scope to develop that sensory motor functionality further. So we're currently developing a sensory motor specific version of the suit. For these mechanical loading countermeasure suits, their relationship of the mechanical properties and the dimensions and shape of the body means that accommodating anthropometric changes with duration and space are important, as are improving the comfort of these garments. And of course, validation studies are required, although some of these will be challenging in terms of time and resources. For example, looking at bone demineralization, and if suits like these can mitigate those changes, then they require longer duration studies such as bed rest. I'd like to finish up by acknowledging our project funding through the ASA's International Space Investment Expand Capability Grant. I'd like to acknowledge our domestic and international collaborators and agency contacts that are assisting in the development of these garments, and thank you for paying attention.